Okay, welcome class to Physics 390 Class 10. This video will be on bases and Dirac notation. Bases are different sets of vectors we can use to underpin wave functions in Hilbert space. And Dirac notation is a very handy notation which enables us to do a lot of things like construct things called projection operators and make transformations between different representations of the wave function in a very convenient way. This is based on chapter 3.6 of the textbook. So bases in Hilbert space, what are we talking about here? So let's first talk about a more kind of definite vector, a geometric vector. So a geometric vector like this vector A here, which is just sitting in space. But that vector can have different components depending on the axes or so the basis vectors that we use to write that vector. So in this example B, we use x hat and y hat to determine the components ax and ay of this geometric vector A. And so we get an ax, which is pretty small, and an ay, which is pretty large in terms of components. But if we took that same vector in space, and instead of using x hat and y hat for our basis vectors, we use x prime hat and x and y prime hat, which are at an angle here. That same vector you can see now has ax prime, the component along the direction of x hat prime, longer, or a little bit longer than ay prime. So depending on how we resolve the vector into which basis vectors, x hat and y hat, or x prime hat and y prime hat, we get different components, even though it's the same geometric vector. Okay. And so that's the idea of different bases. It's the same object, but it's represented by a different set of numbers, ax, ay here, and ax prime, ay prime here, depending on the basis. So similarly, the same state vector, s of t in Hilbert space, remember Hilbert space is the space that wave functions live in, can be written with respect to different complete basis sets of the Hilbert space. Okay. So for example, we showed that any Hermitian operator, the set of eigenfunctions for that operator are a complete basis, a complete set of to express any vector in. So the basis of position eigenfunctions, we would just take the state vector s of t in this bracket notation, and then put the component of that along x, and that would just be equal to our normal wave function. Okay, so if we take the if we write the state vector s in terms of x, we just get our wave function back again, our normal position space wave function. But there are other possible bases. The momentum is another Hermitian operator. So the set of all momentum eigenfunctions is another complete basis set. And so we can take that same state vector s and write it in terms of the momentum eigenfunctions by taking this inner product of the momentum wave function with the state vector. And then we get what we call the momentum space wave function, phi of p and t, okay? And later on, we'll show how to use Dirac notation to go back and forth between these. We've already seen the formula in a previous lecture, but this will be a nice usage of the Dirac notation. Finally, we have energy eigenfunctions. That forms a complete set. So, because energy is a Hermitian operator. So assuming that the energy eigenfunctions are discrete, like for the infinite square wave, for example, if we project the wave function in Hilbert, or the vector in Hilbert space onto those energy eigenfunctions, we get a set of coefficients Cn of t. And those evolve in time with exponential time dependence. So all of these three representations, these are all three representations, one with respect to position, one momentum, one with respect to n, which indexes the energy eigenfunctions. All of these represent the same object projected onto different bases, just like this. These numbers here, ax and ay, and ax prime and ay prime, represent the same geometric object A projected onto different bases in the two-dimensional plane. Okay, so this is a nice way to look at the different representations of a wave function of the abstract state vector S. Okay, so what about operators? Remember, operators act on state vectors, and they can represent physical observables. At least all physical observables are represented by operators. There are operators which do not represent physical observables, but all physical observables will be represented by operators, in fact, Hermitian operators. So anyway, written with respect to a basis, like the position basis or the momentum basis or the energy basis, which we've been just talking about, an operator carries out linear transformations on vectors. Okay, so this is where we see the linear algebra aspect of quantum come in. So with a basis, which we'll just call a general basis, En, okay, this is the set of basis vectors, and an operator Q, it turns out we have matrix elements that define Q. So we would take Q, act on En, and then take the inner product of that with Em, and we get a number, in general, a complex number. And then we do that for each M and N, and we'd have a matrix QMN. And the elements, individual elements, are called matrix elements. So let's see how that works in spelled out. So here's a vector alpha, and it's acted on by an operator Q hat, and we get another vector beta. Okay, so we're going to represent beta in terms of this basis En. So we write it as a sum over n of coefficients Bn times the basis vectors En. So that beta for B for beta is the coefficients B represent beta. And then we write alpha as the sum over n of An En vector. And so acting on that, we would get Q hat An En, but An is just a number, so we can move that Q inside to the right of the An. And so we get this equation here, which is just writing out this equation in the En basis. Okay, now we're going to take the inner product of this equation with Em acting on the left. So just acting it with Em left bracket on the left on both sides. So this becomes Bn Em En, moving the Bn out since it's just a number. And then this becomes An Em Q En. Okay, so you can see how this Em Q hat En arises. It comes when we expand the equation for an operator acting on a vector in a given basis set and take the inner product of that with another vector. We naturally get this expression, which is going to be a matrix of numbers indexed by M and N called matrix elements. So then we can write this since Em and En are different. Well, they're different. They're both part of the basis, and we know the basis must be orthonormal. Em En inner product is going to be delta Mn. And we multiply that by Bn, so we get sum over n Bn of delta Mn, is equal to the sum over n of an, and we call this the matrix element QMN, according to this definition here. So finally then, if we sum up over Bn delta Mn, this is only going to be, Bn will only be count if n is equal to m. So we can replace this side by just Bm. And this side we usually write with QMN to the left of AN. Since they're just numbers, we can do that. So we get finally, Bm is the sum over n of QMN AN. And that's a linear algebra. This is saying the vector Bm is equal to the matrix QMN times the vector, or the matrix representing Q times the vector representing A in the basis En. Okay, so this is seeing in terms of a basis, an operator becomes, has matrix elements and becomes a matrix. Okay, so that's where the linear algebra comes in. Now, many quantum systems have a discrete infinity of basis vectors, okay? And most of the ones we've looked at so far have, in fact, all of them have. So the infinite square well, for example, the energy basis is labeled by n equal 1 up to infinity. So it has a discrete infinity of basis vectors. But there are some quantum systems that have a finite number of basis vectors, such as something we'll look at coming up, which is and we've talked about, you've seen in modern physics, which is the intrinsic spin state of an elementary particle, for example, a spin 1/2 particle. And that has a finite set of basis vectors, okay? So it's in a sense, a little mini quantum system. And they're nice to study because the matrices are not big. They're small and they can be written in conveniently. So just a little preview of that. We'll look at it in more detail in a class coming up. But there's basically two basis vectors for the spin 1/2. Spin up, which would have the 1 up here, and spin down, which would have the 1 down here. And that would be 1 and 2, which would be spin up and spin down. And then an arbitrary state S would be written as some multiple of spin up plus some multiple B of spin down. So that would just be AB. And then to normalize it, we just want A squared plus B squared is equal to 1. Okay. And then operators like since the vectors are basically two elements here, the operators would be like the energy operator, the Hamiltonian, would be a 2x2 matrix in this representation of spin up and spin down. That's not shown here, but we'll see that in more detail later when we look at the quantum mechanics of spin. Okay, let's talk more directly about Dirac notation and bras and kets. Okay, so Dirac had this nice idea to divide up the inner product or bracket alpha beta into the bra, or the first part bra, and the ket beta. And our author makes the joke, we don't know quite what happened to the C. We've got the BRA and the KET, but the C seems to have disappeared. But anyway, that being said, this is very convenient to have a name for these sort of left acting vectors on the left. They're called bras. So kets are normal vectors in Hilbert space. So they represent, they're abstract representations of wave functions, not in any particular basis, but they can be projected onto a basis, or they can be represented in a number of different bases. Bras are actually functions on kets, which return complex numbers, okay? So the bra on the left here, it has to act on a ket. And when it acts on a ket, it gives a complex number because the inner product, say alpha beta, is a complex number. Okay, so for example, usually a bra is an instruction to integrate. So if we have, instead of alpha or beta, we have F vector on the left here, that's an instruction to integrate f star times whatever comes to the right here, so whatever ket comes to the right here, dx. So that inner product there is what we've come to be. That inner product there is what we've come to get used to for the normalization of the wave function. So if we had f bra f ket, we would just get f star f, and that would be our normalization integral. But this is generally, a bra is an instruction to integrate in this inner product sense. Although with a finite basis, it turns out to be more like, as you might expect, with an infinite basis for the quantum system, you would be integrating. With a finite basis, you'd be summing. And it's kind of a dot product like sum. So if now we have, again, beta and alpha, but here with alpha, the ket, so the ket being A1, A2 to AN in a certain basis, and the bra B being B1 star, B2 star, Bn star, star because it's complex conjugate, because this beta's a left, it's a bra, so it's on the left, so it's a complex conjugate. Then when we take the inner product of these, we just multiply each component here. It's like a dot product. We take B1 star times A1, add it to B2 star times A2, and etc. So this integral here becomes a sum over the components of these, the bra and the ket. Okay. So bras enable creating some useful things. There are things called projection operators, and projection operator is defined as the multiplication of a ket times a bra of the same vector. And this has the effect of picking out the portion of another vector. So it's an operator, it's going to operate on another vector, picking out the portion of another vector which lies along alpha. So we would have, for example, P, the projection operator alpha alpha, acting on beta. So we'd get, putting in for P alpha alpha, that is alpha ket alpha bra, we'd have alpha ket, the inner product of alpha and beta. And this is a complex number, so we can move it to the left. So what we're left with, we get a vector along the direction of alpha, since it's projecting onto alpha, but it's the amount of alpha which is present in beta. Okay, so we take the inner product of alpha and beta to get the amount of the amount of alpha which is present in beta. Then we multiply by alpha to get the vector along the direction of alpha in the Hilbert space. So we project beta onto alpha. That's the projection operator. And that turns out to be very useful. So for a discrete orthonormal basis, again, using En as just a general terminology for it, it turns out we can express completeness just saying the sum over all of these projection operators onto all the different parts of the basis is equal to 1. And that kind of makes sense, because if we project onto every possible part of the basis and multiply by the basis vectors, we've covered all the possible components that a given vector can have. So it'd be just like multiplying the vector by 1, because we're projecting onto all the different basis vectors, multiplying by the basis vectors. So just as an example, for the infinite square world, or ISW, the energy eigenstates, which we'll call n here, so n equal 1, 2, 3, 4, and 5 up to infinity, we can write a given wave function psi inside the square well. We can say, we can put in the sum over n and n ket n bra, on psi. But if you look back to what we did here, this inner product of n on psi is what we mean by the component Cn, okay, the component of the n vector ket in the expansion of psi. So this becomes sum over n Cn n, but that's just equal to psi, right? Because this is summing up over all the different basis vectors of how much of each basis vector is there. So that's equal to psi. So we have psi equal to psi here. So that means this sum over n of n ket n bra, that must be equal to 1 because we have psi equal to psi. So this operator must be 1. So that follows that it's equal to 1. And that's a really nice notation for expressing completeness, that the sum of all the projection operators in the basis is 1. Okay. So Dirac notation, very useful and very compact. Let's wind up by talking about using Dirac notation to change basis. Okay, we've talked about how we can write things in different basis. How can we change basis using Dirac notation? Okay, so we just saw that the identity operator, that is 1, can be written as a sum of projection operators for a complete set of states. Okay, so 1 would be, for example, what we just saw it was equal to the sum over n ket n bra in the previous example. But for x, for the momentum, sorry, the position of the momentum, since those are continuous variables, instead of summing up over n, we would integrate over x all of the projection operators because x is a continuous variable. So this would be the completeness relation for the position basis, and this would be the completeness relation for the momentum basis. Okay, and all of these three are equal to 1 because each of these is a complete basis. Okay, so we can use that to write the same state in 3 different forms: the position, momentum, and energy space forms. Position space, momentum space, and so-called energy space. So if we take the state vector s of t, and then we just insert 1, which is the integral dx x ket x bra here. So we've just inserted 1 in front of s of t, so it's an equality. But then remember, we talked about earlier that s of t inner product with x is just the wave function. So this is the wave function psi x of t. So we get the integral of the wave function times the vector or the ket x dx. So the wave function is the component of a given Hilbert space vector in for a particular x basis element. So we sum up integrate the wave function and multiply it by the position state x, and we get a representation of the Hilbert space S of t. We can do the same thing for momentum because the integral of dp p ket p bra is equal to 1. So we just insert that here. But we saw earlier in this video that S of t inner product with p is the momentum space wave function. So we have integral of phi p of t p ket dp. That's another way to represent this wave function. And then finally, we can insert this sum over n ket n bra as the sum of the projection operators. And n s of t we called Cn of t, the component, or not the component, but the inner product of s of t with n. So that would be sum over n Cn of t n. And that's another way to represent the Hilbert space vector S of t. Okay, so 3 different ways three different equivalent ways to represent the Hilbert space vector, the vector in Hilbert space, in terms of three different bases. And we recognize the wave function in position space, the wave function in momentum space, and then the coefficients of the energy eigenfunctions here coming in those formulas. Okay, finally, let's do an example. We can find the transformation from the position space wave function psi of x and t to the momentum space wave function phi of p and t very nicely here by using one of these completeness relations. Okay, so we start off by saying that phi of PMT is the inner product of P with S of T. Then we insert in between them just one, which is, that is the integral of dx times the x projection operator. That's the completeness relation up here. That's equal to 1. Okay. Then we bring the P bra inside the integral, which we can do because it's P, it's not x, so we can bring it inside the integral. And so we get, and then we use the fact that, we bring S of t inside too. So we get the inner product of P, the integral of the inner product of Px times the inner product of x S of t dx. Okay. And so but we recognize the inner product of x S of t as the wave function psi x of t. And then here's this P inner product of Px. Okay. So, but we're actually familiar with that. We've looked at it before when we looked at the the eigenvalue equation for momentum. So Px would be, anytime you switch the bra and the ket, you just get a complex conjugate. So it would be the complex conjugate of xp, which would be the complex conjugate of the momentum eigenstate expressed in the x coordinates, which we called fp of x, complex conjugate. So this we found before. It was 1 over square root of 2 pi h bar e to the I px over h bar. So when we take the complex conjugate, we just change the I px over h bar to minus, and we get 1 over 2 square root of 2 pi h bar e to the minus I px over h bar. Okay, so so we've got the px here. Now we can plug that in here and substitute in here and find that phi p of t would be the integral, substituting in this 1 over square root of 2 pi h bar e to the minus p x over h bar here for the inner product of px times psi x of t dx. Okay, now we actually had this formula before, but it took us a while to derive. And here we've done it in, well, 3 or 4 steps by using this, our knowledge of the momentum eigenstate and this completeness relation, by putting this completeness relation inside the momentum space wave function. And this is a Fourier transform, right? This is a Fourier transform. The momentum space wave function phi of p and t is the Fourier transform of psi of x and t. And we've gotten that very nicely using the Dirac notation. So hopefully you can see that it's handy. It takes some getting used to. But so just to summarize, we've talked about how we can have different bases for vectors in Hilbert space. The main ones we use are position and momentum and energy. And it's just like representing a geometric vector with different sets of basis vectors in the plane. It's the same basic object, just written in terms of different bases. We've looked at how operators become matrices when they're written in terms of a particular basis. Okay, so they become matrices. We've looked at how the quantum systems we've seen so far have an infinite bases, either discrete, infinity or continuous infinity, but there are systems which we'll look at mostly involving spin, which have a a finite basis. And those would be, the operators would be finite matrices in that case. So we really get into linear algebra there. Then we looked at the bras and the kets, dividing up just giving names to these left and right vectors. And so we have a terminology, the bras and the kets. And we saw how the bras act on the kets in terms of as an instruction to integrate, or in the case of a finite system, to take a dot product. And then finally, we saw these completeness relations with the projection operators, that if we integrate or sum over all possible projection operators, we get 1, because that's the same as projecting onto every state in the basis and multiplying by that state. So that's the same as multiplying by 1. And then finally, we see with the Dirac notation how it's nice to switch between different position space and momentum space. Okay, thank you for your attention, and I will see you all in class.